Okay, welcome back to Love and the Physics with Mr. Goldthorpe. So here's our last lesson for energetics. We're going to talk about power and efficiency. And here's a really important question in the area of Physics 20. We have the same vehicle in all these three different paths, and they're all going to go up at basically the same speed, a constant speed all the way through. So just keep in mind, they're all basically going up at the same constant speed. And our question is, which route would you expect, A to D, B to D, C to D, which one would actually require the most gas? Which one would require the most work? Think about that. Pause. Now the answer might actually surprise you. And it comes from this idea right here. Imagine we have a car going up at a constant speed up an incline like we see right here. Now you could, if you wish, conceptually think about dividing this up into two parts of motion. One, which is a horizontal motion, and two, which is a vertical motion, and it takes it to the same location. Now what you need to understand is that when you deal with the horizontal motion, if it's going at a constant speed, then it turns out that the horizontal part requires no work at all. It wants to go at a constant speed all the way through. And so no work is actually required to move this thing horizontally. So therefore we can ignore the horizontal part of the motion. And therefore all the work is done in the vertical motion. And of course, we're ignoring the effects of the force of friction and gravity. We're ignoring the effects of air resistance in this one here. And so therefore, we only have to think about the vertical. And the idea is because vertically, that's where you have a change in potential energy. So work is actually being done. So when we go back to this original diagram, can you see they all are going through the same vertical motion? It's the same height for all of them. And as a result, surprisingly, they require the same amount of work. No matter if it's steep, no matter if it's a shallow incline, or whether it's circuitous going up in an S shape, makes no difference. The work will basically be the same. Shocking. But surely there has to be something different about these. And it turns out the key difference is how much time it takes. Now I hope you can see that if we go from A to D, and I'm just going to put this on here, if you do the A to D part right here, do you guys agree this will take the least amount of time? And if you've ever done any kind of hill training, you know that this one from A to D is what we call the hardest to do. Now, how hard it is has nothing to do with work, and time has no effect on work. So what accounts for how hard these things happen to be? And it turns out the answer is power. It turns out from A to D, that one actually requires the greatest amount of power. Whereas something like C to D has a lot less power required. And this is our new topic, power. So you can basically think of power as how quickly we do the work. And it should be known that this is a scalar quantity. So notice it is work over time, or change in energy over time. Can you see that power and time have an inverse relationship if the work stays the same, as it did in that previous example? Therefore, the smaller the amount of time, the greater the power required. If you want to get up that hill really quickly, then you require a lot more power. Makes sense, hopefully. And the units for power are in watts. Unfortunately, that uses the same letter W as work, and that can be kind of confusing. But I should actually show you the equivalent unit here. I'll try a different color. Based on power is equal to work over time, if we do power is equal to work or change in energy over time, it follows that a watt will be equal to a joule per second. And this actually helps us understand when we're given power in watts. For example, if you have a computer and let's say it's operating at 10 watts, well, that means it's consuming 10 joules every second. As opposed to, let's say, your your music system, let's say it's ranked at like 500 watts. Or your microwave, which might actually be 1500 watts. If it's 1500 watts, that's 1500 joules consumed every second. Good? So I think that's actually helpful. Now it turns out that when we're typically doing work, we often, if we have, let's say, an object here, when we're doing work, we typically apply a force and we move it from one location to another, like pushing your desk across the room with some force F. And if we're smart, we'll go across at a nice constant speed. That's how we typically do work. We call this minimum work. And if you have a situation like that, there's another way of actually finding the power. Because remember, power is equal to work over time, but work is equal to FD in this case, because it goes the same way as a motion. So now we have FD over T, which rearranges to F times D over T. And notice D over T is the average speed of the object. So we have another way of finding power, equal to F times V. And we do that if it's moving at a reasonably constant speed like you see in my diagram on the side. So if you have an object moving an object at a nice constant speed, if you have a force applying on an object and moving it at a constant speed, then this is a pretty good option, F times V, because we often want to know what the force, well, anyways, let's not get into too much detail. Use that formula if it's appropriate. All right, let's try an example of this. So we're going to use an electric motor to lift an elevator. And again, we typically lift elevators at a nice constant speed. That's a nice way to experience an elevator. You don't want to have it jerking up with high accelerations. So let's draw this. This is our 1500 kilogram elevator, and we're moving it up to a height of 10 meters. And we're told that that elevator requires 8.2 kilowatts, and it's going at a nice constant speed all the way through. And we're trying to figure out how much time it takes. Now our governing equation here is we know that power is equal to work over time or change in energy over time. Whichever one you want to do. They both will work. Let's take on the change in energy idea. So what we can say is we can say that the work done by this motor will actually change the energy of the system. Well, what kind of energy is changing? Well, there's no doubt there's a change in height. So there'll be a change in potential energy. And you might be tempted to say, well, hey, there's speed, so there's also going to be a change in kinetic energy. Now, you're right that there's kinetic energy, but to change, can you see the speed has to change? But this is going at a constant speed, which means there's no change in kinetic energy. So all we have is simply change in potential energy. And we can call that EP final minus EP initial, or mgh final minus mgh initial. And it kind of makes sense to choose the lowest location here as your zero height location, so it actually has no height at the start, no potential energy at the start. So therefore, the work done is simply going to be the mass, which is 1500, times 9.81 times the 10 meters that it actually goes up to. So let's multiply those out. So we get like 147,150 joules of work being done on this elevator. All right, let me just add one more page. And now we can take on our power formula. So just remember that power is equal to work over time. And we're trying to solve for t. So that we multiply, cross multiply. PT is equal to W. And therefore T becomes equal to work over power. Now work was 147, 150. And the power, we're told, is 8.2 kilowatts. And remember, the unit for power is watts. So don't forget to change that to standard units. So you can call this 8.2 times 10 to the third, or 8,200 watts. So divide this by 8,200 essentially. And the time, and let's see how many sig digs we're going to give ourselves here. Looks like 3. So the time comes out to be 17.9 seconds. Okay, well, I think it's actually useful for you now to go to the homework and just try some basic questions involving power. Like the first few questions in the homework, and then you can come back and actually take on the second part of this lesson. I'll see you then.